Hi, and welcome back to another video with It's Dr. Dan, and today we're going to be looking at gas evolution reactions. So when in our previous videos, when we talked about aqueous reactions, we saw that different solutions, when they're mixed together, they can make a bunch of precipitates. Well, one of the reactions I mentioned is that they can also form different gases. So whenever you have a gas as a product, one of the things that we need to try to do is realize when can we label it as a gas, because that's something that's not going to pop up on your solubility rules. And on top of that, they're going to be in the identity of a different type of compound. So we're mainly going to be looking at these different double displacement reactions. So AB plus CD recipe style reactions. And we're going to be looking at four main gas evolution products. We're going to go through multiple different types of examples to show how we can see these and how we can predict them for chemical reactions found in your introductory chemistry class. So, what are all the different types? So, with these, there are four main things you're going to be looking for. So, if you see them, you're going to have to essentially erase them and change them. So, the first one is whenever you see carbonate. So, if I have, for example, H2CO3 and I have the carbonate polyatomic, well, that's giving you a big red flag that it needs to be changed. So whenever this is in solution from the double replacement reaction, it's going to be making two different things. The H2O and CO2 are going to split off because one of these is a gas. So what does CO3 look like? Well, that's going to be CO2 gas. So that we'll label with a G, and then we'll also have water. So it's going to make water and gas as a result. So H2O is a liquid and CO2 as a gas. Now, another big type that we're going to see is whenever we have the polyatomic sulfite. So let's label these. So we have carbonate. Our next one is whenever we have sulfite. So if I have H2SO3, and I'm trying to see, all right, if I have this aqueous product formed in a reaction, once again, we're going to be making water as one of our products. And then what is left over if I subtract, if I kind of think of this as a subtraction problem, if I take H2SO3, subtract H2O, well, what's going to be left is SO2. So we're going to make sulfur dioxide gas as a product. So that's going to be other hint that we're going to be looking for. Another big polyatomic that we're going to be looking for is whenever we have ammonium as one of our polyatomics in a product. So in this one, right, we had, let's see, SO3 in the last one. And then if I have ammonium in the very beginning here, well, what this is going to further break down into, so instead of having ammonium hydroxide, it's going to make ammonia gas. So ammonia is NH3 gas. And on top of that, well, what's going to be left over? You might have guessed it from before based on the previous trends, is water. So these are all the different types of reactions where it's going to further break apart. There's one other molecule that does commonly come up when it comes to double replacement, and luckily this is a little bit of an easier one. It's whenever we have H2S as a product. Well, whenever that is one of our products, that one is going to remain as H2S. Okay, so instead of it being written as aqueous, this is going to be written as a gas. Okay, so that's what you're looking for when we go through all these, is these different gases, these different little ingredients that we have. If it's carbonate, sulfite, ammonium, H2S. These are types of things I would recommend putting them on flashcards for yourself, because these are the four gas evolution products that if they come up in double replacement, that particular product further breaks down and it makes it a little bit more complicated reaction. So we're going to go through a couple examples of this to show how can we balance it, and then how can it be implemented in a net ionic equation as well. So we'll look at the whole picture for you. So let's do some examples first. So let's say if I had HCl or hydrochloric acid mixing with sodium carbonate. So in this one, right, all these are all double displacement. So if I have AB and we're going to be adding that with CD, we're going to do outside inside so we can predict how these are going to be. So our outside is going to be H plus and then CO3 2 minus. We're just trading those ions. We'll swap drop it. So as a result, it's going to be H2CO3. Our other product is going to be the inside. So that will be B and C coming together. So that's going to be sodium plus and chlorine minus. So as a result, as you can see, if we swap drop those charges, they're already balanced. We already have a +1 with a -1. We don't have to do anything with swap dropping with subscripts. Now, one thing we have to check is this a balanced chemical reaction? So one thing before we even balance, you'll notice already is that one of our products has the carbonate ion in it. So it's telling us, okay, this thing's going to further break down. But one thing that's a really good tip to try is, can I balance it before breaking it down? One thing, if we can do that, it might make balancing this equation a little bit easier when you write the actual products. So if I look at these, I can see, all right, carbonates are balanced on both sides. We can look at the sodiums next. So if I look at sodium, on here we have 2 of them. We only have 1 on the right, so we will put 2 NaCl. That means that we'll then switch zigzag over to the chlorines. We have 2 on the right-hand side. So we'll go to the left and we need 2 over there, and it balances the whole chemical equation for ourselves. Now, one thing that we have to do is rewrite how our products are going to break down. Because H2CO3, we need to erase this product. That is not how it's going to be formed. One thing that we can see is H2CO3 is our first example. It's going to further break down into CO2 and water. So when we write this, we will write that we have H2O, which is a liquid, CO2, which is our gas, and this is going to be in addition to the 2 sodium chlorides that were there in the beginning. So all the products still remain balanced. Everything works out with what it originally had, but instead we have extra products that are going to be forming. So in this case, if you mix some things in a test tube together and you saw some bubbling occurring in your experiment in the lab, well, that's telling you that that's the gas that is forming. So if you ever see bubbles coming off of a test tube or any type of different type of reaction, well, that is realistically what you're going to be looking for when you're going through all these kinds of examples. So what other types of reactions can we see? Well, what if I gave another one where I had ammonium chloride, so NH4Cl, and that's reacting with sodium hydroxide. What about this one? What kind of products am I going to make? Same idea. We do inside, outside. So inside, bond together. So that's going to make sodium chloride. Then we have outside, bond together. And that's going to make NH4OH minus. Everything is already balanced in terms of charges. Now, what we're trying to do is there anything here that's going to further break down? And one of the things you might realize is, whether you notice or not, is ammonium was one of our culprits. So number 3 was ammonium. So being that ammonium is going to further break down into NH3 and H2O. So why don't we write that down? So when we go back to our example, what is going to be happening is we're going to be getting rid of the ammonium here, and instead we're going to be showing that this reaction is going to be making NaCl and ammonia gas and water. So this is what we are showing in our reaction here. So it's something that it can be really involved. It can have all kinds of different examples of how we can show this. But why don't we try to do two more of maybe a slightly harder type of example. So if I tried to instead, let's say, give you a question where I say, let's have sodium bisulfite. So we have Na bisulfite, and this is going to be reacting with HBr. So how would we actually look at this type of example? So a sodium bisulfite HBr, we're going to follow the same steps. Now, when we do this, we're going to do inside, outside. So when we have inside, outside, we are going to have sodium bonding with bromine. So it's going to make NaBr. And then we're going to have, where we have bisulfite reacting with hydrogen to make H2SO3. Now, in this reaction, we would check our solubility rules just like always. But bromines are soluble, so are sulfites. So, but something is going to further happen. We see bubbles from this particular reaction. Something is not quite adding up, being that we have little bubbles in there. So what is going to break down? So let's take a look at our list from before. And one thing that we can see is that, okay, well, I have sulfite in my reaction. That's one of our polyatomics. That's the little red flag that's going to be going up and down when we are doing this. So H2SO3 is going to break down into SO2 and water. So why don't we write that down? So with that, this is going to further break into more products. So we'll rewrite our products. The first thing is NaBr. So alkali metals are always soluble. That's part of our ANA abbreviation. And then H2SO4 is going to break down into H2O as water, and then SO2 as a gas. Now, let's say I ask you, find the net ionic equation, which if you refer to my last video on net ionic equations, this should illustrate something being formed. So with those, they always show how precipitates are formed or how gases are formed. So what this should do is it should help show how SO2 and water are forming. So let's do that. So if the beginning of this reaction said that two aqueous solutions are being mixed together, so sodium bisulfite, HBr. The way that we can tell they're soluble is alkali metals, so sodium is always soluble. So this thing is aqueous. Bromines are always soluble with H, so this is also soluble. So let's show the complete ionic equation. So when we do that, we would have Na plus HSO3 minus. Then our other reactant would be H plus Br minus. Let's write that this is a complete ionic equation. And what this is going to be breaking into is NaBr is also soluble based on our solubility rules. Na plus Br minus. Now, is water soluble? Well, is water soluble in itself? Well, we just leave it as water. So H2O is going to remain as a liquid. And the same thing with SO2. That's also going to remain as a gas. So now what we're going to do is, in order to get to the net ionic equation, we're going to eliminate all spectator ions. So if you remember, spectator ions are what's on both sides of the reaction. What is the same? Well, if you look closely, you'll see that sodium is the same on both sides. So that goes away. And then we also have that bromine is the same on both sides. So that also goes away. So what is left is illustrating the H2SO4 breaking it down. So our net reaction is HSO3 minus plus H plus leads to the formation of water as a liquid and SO2 gas as a product. So we can also show net ionic reactions as well, which is really exciting to see. So why don't we try to do one more to wrap up all 4 of our types of examples? So there's one that we did not show. What if I give you the following balanced reaction? So if I tell you the following, so if I give you a new question, and I have Li2S, so lithium sulfide, and that's going to react with HClO4, and that's going to yield H2S and lithium chlorate. All right, now I'm going to balance this for us, and if you'd like to practice balancing it, I would fully recommend it, but we're just going to look at the net ionic equation. So with this, what is soluble? So going off solubility rules, a couple things is remember the abbreviation ANA, alkali metals, ammonium, nitrates, and acetates are always soluble. So by looking at this, right, we can see we have a lithium here, so that's soluble. Then with chlorates, this one is soluble as well. Chlorates are on there. This one would be soluble. Now we have another alkali metal, so that is soluble too. Now what about H2S? Well, H2S was our 4th gas that if it ever forms in a product, that this would be a gas. So in this particular reaction, we can label it with a G telling us, all right, well, all of these other ones are aqueous. So this is your complete molecular equation. Now let's do our complete ionic equation. So the complete ionic equation, what it does is it takes all the aqueous components. It tells you that water bond or hydrogen bonding doing ion dipole interactions all around it are stronger than those ionic bonds that they dissolve. So what we're going to do is we're going to break down all the reactants. So we have 2 lithium ions with 1 sulfur ion for lithium sulfide. These are all aqueous. Then we have 2 hydrogen ions with a chlorate that is also aqueous. There's 2 of them as well. And then we're going to show that H2S gas is being formed. And when we show that another color, just so we can highlight that H2S is a gas. And then we have 2 lithiums plus 2 chlorates. Okay, so what is going to cancel out? So we're trying to look at what is a spectator ion on both sides. So what this thing right now is showing is the complete ionic equation. So the net ionic equation, which is our last thing, is going to eliminate the spectators. So it's whatever is watching and not participating in the actual reaction. So one thing you'll see is that, okay, we have lithium on both sides. It's not doing anything. We also have the chlorates, which are here and not doing anything. So the one things that you see left are sulfur and hydrogen are going to be left. So what we'll have is S2 minus aqueous reacting with 2H plus aqueous leads to H2S as a gas. And that would be our final answer for this problem. So this is how you can go through all the different types of gas evolution problems. This is an example for all 4 types, and also doing net ionic equations, which is a really common practice that you might have to do in the lab. I hope that this helps for you to be able to try to predict different reactions, being that different products can always be forming. And keep an eye out for future videos. Please hit that subscribe button to help support helping all chemistry students like you learn future content like this. All right, and I hope you all have a wonderful day, and I'll see y'all later. Bye now.